Okay, chapter 24 is now going to concern us with magnetic fields and magnetic forces. This follows the discussion of electric charges and electric fields. And there are similarities between the two, but there are also big differences between the two. And so let's talk a bit about magnetism before we get into a discussion of magnetic fields. You'll recall that for electrostatic fields and electrostatic force, the fundamental charges are the plus and the minus. Those are the fundamental charges. We learned that electrons are negative and protons, which make up the nucleus, are positive. And we also learned that like charges repel, so positives repel positives, negatives repel negatives, and then unlike charges attract. That's what we learned about the electric force. And it's very similar in the case of magnetic forces or magnetism, with a slight difference, and that is that while like poles do repel, north poles of bar magnets repel north poles, and south poles repel south poles, it's also true that unlike poles attract, and so far it looks very similar to the case for electrostatics. However, these poles are not individual and separate as they are in the electrostatic case. In the electrostatic case, positive and negative charges have a separate identity and they attract one another, the positives and the negatives. In the case of magnets, you can't divide a magnet into north and south poles. They're always joined together. Every single bar magnet in nature has a north and a south pole, but if we were to cut that bar magnet in half, rather than having a separate north pole and a south pole, we end up with two magnets, both of which have a south and a north pole. It's a little mysterious, but the reason behind that is because if we continued cutting this magnet into smaller and smaller pieces, we would end up producing smaller and smaller bar magnets until we got to the point where we had one single atom. And it turns out that one single atom of a bar magnet, for example iron, a separate individual atom of iron, has its own magnetic field, its own bar magnet nature. And we can't split the atom in two because that would require breaking up the nucleus, for example, or taking electrons away from the iron, which would not change its magnetic character. So even atoms that are magnetic, that make up magnetic materials, and a good example of that is iron, it's the very atoms that are little magnetic dipoles. So when they combine to form a large magnet like this, they're bound together in a solid, they pretty much line themselves up with one another, so all of their little magnetic fields add into one big magnetic field for the bar magnet. But then that helps explain why when we break a bar magnet in two, all we're doing is we're breaking the collection of magnetic atoms in two, in which case each of the separate pieces that results from that cut will still have lots of magnetic atoms that line up with one another to produce this bar magnet. So one of the truths that, so far as we know in modern physics, that we need to establish is that there is no separate identity between a north and a south pole. They're not two separate entities. They always come in pairs. Magnets always come in pairs. And so since the north and the south poles are not the elemental charges of the magnetic field, or the elemental particles, the elemental particle actually is the magnetic dipole that already has a north and a south pole. So the individual particle that makes up magnetic fields or magnetic systems or magnetism is the dipole itself. And as I said, that dipole goes all the way down to the atom. The individual atoms are themselves magnetic dipoles. So in bulk, when they form a solid, they will form a large bar magnet with a clearly identifiable north and south pole, but these are at the ends, and we'll study what the field looks like for those in just a moment. One of the ways we can tell which is the north and south pole is by using a compass, but it requires that we already know which end of the compass is north and which end is south. The magnetic north of a compass is depicted in red here, and the south side of this bar magnet is depicted in white. And so this whole compass needle is one bar magnet that sits on top of a pin, a small pin, about which it's able to rotate freely, so that under the influence of a magnetic field, like that of the Earth, this compass will rotate to show us the direction of that field. We can use this compass to determine which end of a bar magnet is north and which end is south. If we put a bar magnet up near to this compass and it attracts the North Pole, if it causes a force to line up the North Pole with that end of the bar magnet, then we know that this bottom pole here is the south pole, since unlike poles attract and like poles repel. If, on the other hand, this bar magnet, when we orient it like this, pushes the north pole away and attracts rather the south pole, then we would know that the bar magnet that we are testing, its near pole is a north pole, which attracts the south and repels the north of the compass. So this is one way that we can determine which side of a magnet is north and south, but we have to start with a bar magnet whose north and south ends are known. Another important feature of magnetism is that not only are there bar magnets, but there are magnetic materials. Iron is a good example of a material that is magnetic, so that anything that has iron in it is commonly magnetic. Paperclips are a great example. Paperclips are themselves neutral. They are not little bar magnets, but they can be attracted to a bar magnet. And furthermore, paperclips, since they're neutral, are attracted both to north and to south magnetic poles. What happens is when the paperclip is stuck to a north pole, like right here, the paperclip itself adopts a temporary magnetism where its south pole is located close to the bar magnet, and its north pole is located back here, away from the magnet. So while the paperclips are attached, they are temporarily little bar magnets themselves, bar magnets. But as soon as we detach it from the bar magnet, the paperclips are no longer magnetized, but adopt a neutral configuration. But since this is true, you can also attract a paperclip to a south magnetic pole, in which case the end of the paperclips that are close to the bar magnet form the north pole, and the side of the paperclips, or the end that is away from that bar magnet, form the south pole. But again, once you remove it, it's neutral. Now I want to remind you of something we learned about charges and conductors when we were studying electrostatics. A conductor is neutral, but it can also polarize. The charges can move on that conductor. So if we brought a conductor up to, let's say this circle right here is a conductor, if we brought it up to a positive charge, the near side of the conductor would have negative charges and the far side would have positives. It would polarize, in other words. And as such, it's attracted. There's a net force between the conductor and the charge by virtue of the conductor's ability to rearrange its charges. So in this fashion, one conductor can be attracted to both a positive charge, in which case it would polarize as shown here, or it can be attracted to a negative charge, in which case it would have the opposite polarization shown here. So that situation for electrostatic fields should help us understand why paperclips in a similar fashion can be attracted to both south and north poles and don't have magnetism themselves. Copper, on the other hand, is not a magnetic material here down at the bottom, and so nothing will influence it. No bar magnet orientation will influence it, since it's a non-magnetic material and therefore does not respond to magnetic fields.